Okay, today it's quadratic variations and applications. So we're going to combine what we've learned about direct and inverse variation and what we've learned about quadratic equations in this lesson. Let me get my pen ready here. Let's go with red. So what are the things we're going to do today? Find an equation of direct. Remember, that's when one variable increases, so does the other. In this case, with quadratic variation, it's going to increase. The response variable or the independent variable is going to increase very rapidly. Then we'll have equations of inverse. Remember, with inverse, as you increase one variable, the other variable goes in the other direction. And then we're going to solve some problems dealing with quadratic variation and proportion. We haven't talked about proportion in a long time. Here's our, I don't know if this clock is showing up or not. I better get rid of it. You probably see this, right? I'll get it off the screen. Here we go. This, remember, is a review. You can skip over it if you're pretty good with all of this. This is solving a radical equation. Remember, we can't do anything with what's underneath this radical symbol until we get it released from that radical symbol. The only way to do that, as in all these operations which trap a variable, you want to do the opposite operation. What is opposite to square root? And what we do to one side, we do to the other side. So we end up with x squared plus y squared equals d squared. I want to solve for x. I should really keep my eye on x here. I'm going to move this down out of the way for a moment. And x is having something added to it. What do we say when we trying to release something from an operation? If we don't want something being added to x squared, then we'll do the opposite operation, which will subtract that from x squared. So x squared is equal to d squared minus y squared. I'm not interested in x squared. I want to have x to the first power. So I better take the square root of that. I have to take the square root of the whole of the other side, and it's going to be plus or minus. By the way, congratulations to all of you who always remember that. It's such an easy thing to forget, and I notice that many of you do a really good job with that. You do remember that it's plus or minus when you're doing the square root of both sides. That's supposed to be a d. So that would be how you would solve for x when x is trapped in a radical like that. What if I'm solving for m? And this, we've got m trapped in a little bit different way. You can see that it's in the denominator, not where we want it. So we're going to multiply both sides of this equation by m squared plus n squared. And the wisdom of this is that when I have in my numerator m squared plus n squared, and also in my denominator the same thing, that's equivalent to 1. So I have here a times m squared plus n squared equal to 1. What am I trying to solve for? M. So I've got all of this in a parentheses. I can't touch it until I get rid of this a. A is being multiplied, so I'm going to do the opposite operation, which is, that's right, divide. Then I'll have a over a, which is same as 1, leaving me with m squared plus n squared equals 1 over a. I'm still interested in getting m by itself. Right now it's being squared, but it's also got something being added to it. So I'm going to do the opposite operation, subtract, and I do it to both sides. So we end up with m squared is equal to 1 over a minus n squared. I don't want m squared. I want just plain old m to the first power. So I'm going to take square root of both sides. Yes, I hear you. It should be plus or minus. Good for you. Thanks for reminding me. M equals plus or minus. So that was a little review. I hope that helped you. We're going to move ahead now with what we said we would talk about here, quadratic equations and variation. First, I was going to do a quick review of variation. Direct variation, that's when as one variable goes up, the other variable goes in the same direction. If the ratio is constant, this is our ratio right here. The ratio is constant, unchanging, then y varies directly. Inverse behaves just the opposite. These two variables travel in the opposite direction. As one goes up, the other goes down. In this case, it's not the ratio that's constant, it's the product. So k is a product, and that is constant. When that's the case, you're talking about an inverse variation, and it looks like this. Now, both of these are first power. We're not talking about any quadratics yet. It was a little review of what we learned in 6-9. Back to Chapter 8. Direct variation. Now we're going to talk about quadratic. So what do we see right here? Yes, we've got x squared. As x squared increases, y increases. Because we're talking about direct variation, the constant shows up right here. And we could write it like this. K equals y divided by x squared. You remember a moment ago we were looking at the direct variation. If a ratio is constant, see, here's our ratio. Now with quadratic, again we have a ratio. Find an equation of variation where y varies directly as the square of x. So we know we're talking about x squared. Well, if x is equal to 3, x squared is equal to k. We know it's the ratio of y over x squared. because we're talking about direct variation. So that's going to be equal to 2 over 9. So what does our equation look like? Well, we can look right up here to see what it's going to look like. Y equals k times x squared. And we figured out what k is. It's 2/9. There's our answer. Direct variation, just a little more work on this to see if we really understand what we're talking about here. Direct variation, they travel in the same direction, the x squared and the y. And if we write it as an equation, we see it's y equals k times x squared. If y divided by k equals x squared, is this a direct variation? Well, let's see if we can put it into this form. Y, I could multiply both sides of this by k, couldn't I? And I then have k over k, which is 1. Y equals k x squared. So the answer here is yes. And that's how you can always prove it. Just see if you can get it to take the form of what you know is a direct variation. How about this one? Y times x squared. Can we get that to fit this form? Well, let's see. We're going to solve for y, which means since y is currently being multiplied by x squared, we want it all by itself, we're going to do the opposite operation. Instead of multiplying by x squared, what would be opposite? That's right, we divide by x squared. X squared over x squared is equal to 1. Y equals k over x squared. Now that is not a direct variation. I bet you could tell me right now, though, what it is. Okay, maybe not, huh? Okay, let's go back a minute, because I think if we go back a bit, it will become rather obvious what it must be. Remember, direct variation, we had y equals kx. Inverse variation, what do we have? Y equals, and look where x is. K is being divided by x. So back to where we were. So what do you think this is? I think so too. Okay. Inverse variation. Woo! Hey, this works out great. Look at this. There it is. That's our inverse variation. So let's see what we can do with this. Find an equation of variation where y varies inversely. We know what that's got to look like as the square of x. Well, x squared when x is equal to 3 has got to be 9. So we're going to have k equals x squared times y. I'm going to back up again for a moment because I'm not sure we made this, oops, really clear. Right here, with direct variation, we said that the constant k is a ratio. We know what ratio means. You see the word ratio, you think fraction. And with inverse variation, the product of x and product of x and y. We see product, we think multiplication. So now back to our inverse variation. Sorry, I went ahead too far. It's going to be the product. The constant k is going to be the product of x squared times y. And that's going to be 9 times 2, k is equal to 18. And the way I write this equation, right up here we see the model for it, right here. That's going to be y equals, and we put the constant in the numerator. With inverse variation, my independent variable, x squared, is in the denominator. There's my equation of variation. When you do these, you have 2 steps. You must find what your constant is. Then, using the model, you write the equation with the value for k in it. You're not done until you complete that. Joint variation. This is any combination of variables. So they could be varying directly or inversely. And you can find both happening at the same time. Here are some examples. This first one shows our constant of variation. Notice the constant of variation in the equation. It always is in the same place. It's in the numerator. Now sometimes you look at this, you might not think of this as the numerator, but if you picture it as being over 1, you can recognize that in every case k is in the numerator. So then all we have to do is notice where the other variables are. X and z are also in the numerator. This is a sign of direct variation. So both x and z are varying directly with y. In the case of the next one, notice where x and z are. They are in the denominator, and they are varying inversely. Please notice, as they go up, y goes down. And finally, we have a situation where z is varying directly and x is varying inversely. As x goes up, y goes down. And of course, z, which is varying directly, moves in the same direction as y. So we can get all kinds of combinations. Very interesting. Find an equation of variation where y varies jointly as x and z. Now it's just saying they're varying jointly. So let's look down here. Maybe this will help us out. When the type of variation is not given, they don't tell us whether it's direct or inverse. In that case, you can assume that the relationship is direct. If it is inverse, I will have to tell you that. So that means I can put together the model of this equation. Y equals k, and x and z are going to be varying jointly, and both of them are varying directly. So what is my k? Well, k is going to be, remember, k is always a ratio when we have direct variation. In this case, my numerator has the y, my denominator has x times z, so my k is equal to 1/6. When I rewrite my formula, find this equation of variation, it's going to be y equals, instead of putting k in, now I put in what the value is, 1/6 of x and z. There it is. Now, of course, you could write that a little bit differently. You could write it as y equals x z over 6. I do worry a little bit about writing it this way, because what did we say about k? And I want you to keep this in mind. K is always part of the numerator. This one, this is not wrong, it's just that it might tend to be a little confusing. Let's keep moving. We have some great examples here. Another joint variation. Find an equation of variation where y varies directly. Okay, it's telling us what that relationship looks like. So we've got y equals always k in the numerator, true. And direct means that's also in the numerator here. Oh, z, however, is here. So when I go to figure out what k is, I'm going to have y in the numerator, z in the numerator, and x in the denominator. So my k is equal to y times z, 8 times 5, 40. My x is equal to 2, so k is 20. Let's write that equation now. Y equals 20x divided by z. Very good. Oh, wait a second. That's not so good. Look at that. Square. Did I miss that previously as well? I caught it there. We had the square of x. And then on this one, we didn't talk about squares at all. Boy, that threw me off, didn't it? And then when I read this next one, I didn't read it correctly. I bet you were trying to tell me. I am just so glad I caught it. Maybe I actually heard you. Okay, so this was wrong. This should have been square of z. That's going to change things, isn't it? Because now we've got z square up here. Z square is, what is z square equal to? That's right. So 8 times 25, it's not 400. It's, that's right, 200. I mean, it's not 40, it's 200. And when I divide that, I get 10. And this will be y equals 10, excuse me, 100. Boy, when I make one mistake, I make three. 100x, because x is direct, and inversely as the square of z, so that'll be z squared. So I can demonstrate mistakes pretty darn well, can't I? Okay. So let me know if I didn't get through that correctly. Now I've lost confidence in myself. I better read carefully. I'm so interested in getting through this in the time I promised you that I'm rushing. And you know what rushing does. So inverse variation. X is going up, Y is going down. Joint variation, any combination, varying directly or inversely. And if it tells you it's joint variation and it doesn't tell you which it is, you always assume it's going to be direct. Let's look at this one. If y varies inversely as the square of x, you know, I'm going to be a little more careful about this now. Square. And the square of y. See, I will notice it much better if I put that little exponent on than reading those words. You know, I'm in math class. I'm thinking more about numbers than words. It's not, I'm not trying to make an excuse for myself. If y varies inversely, so that means we'd have y and we'd have k always in the numerator, but my x squared would be here. If this is the case, does x vary directly as y squared? Well, let's find out. So I'm going to multiply both sides by x squared in order to reposition x. I'm actually going to solve for x. And I'll have x squared y equals, and of course x squared over x squared is 1. So that equals k. And now I'm going to divide everything by y because I really am trying to get x all by itself. So I'll have y over y, which is equal to 1. X squared equals k over y. I'm interested in x, so I'm going to take the square root of this. Yes, plus or minus. So x is equal to plus or minus the square root of k over square root of y. So no, this is definitely a no. X is varying inversely, right? Inversely. And it's not as the square of y, it's as the square root of y. This is a total, oh, I even have to put this in red. This is going in red. No. Okay, let's see what we can do with this last question on this page. If y is equal to xz, what is the constant of variation? Is it that we don't have a constant of variation? Answer, no, Mrs. Turner. We do have a constant of variation. What would it be? What is the coefficient that we never bother to write down? Well, rarely bother to write down. That's right. So don't let yourself be tricked by this one. In this one, we still have a constant of variation. It's equal to 1. And just for the fun of it, let me throw in another one. If y is equal to negative xz, what is the constant of variation? Thank you. See, you guys are better than I am. Quadratic variations and applications. Oh, yes. I mean, this is where they actually come into our lives in real life. The current I in electrical circuit varies directly. So let's see if we can write that down. It's actually what I studied when I was going to college. I in electrical circuit varies directly. We know where K is, right? K is always in the numerator. And if it's a direct variation with E, then E is also in the numerator. And inversely, which tells us that it's going to be in the denominator, as the resistance R. The current is 2 amps when the voltage is 8 and the resistance is 4. So we can use all that information to figure out what K is. Now, let's take a moment and write out K. K would be I times R divided by E. The I is 2. Right, that's my current. 2 times the resistance, which is 4. So I've got 8 amps times 4 ohms is 8, divided by E, the voltage, which is 8. Oh, this is the one we were just looking. Well, it isn't the same equation, but we have a K now that is equal to 1. Find the equation of variation. Okay, we can do that. We've got the current is equal to, isn't that nice to have 1? We don't even have to write it in there. E over R. So the current in amperes is equal to the voltage in volts divided by the resistance in ohms. What is the current when the voltage is 10, E is 10, and the resistance R is 20? I think we would write that as 0.5 amps. I hope you could read that, 0.5. We have one more word problem here. This is about light intensity, and this actually gets us into a quadratic. Back here, we were just talking about inverse and direct. This was joint variation, but we weren't doing anything with quadratics. But this one, we do. We've got the intensity of the light. So now we have a new meaning for I. It's no longer current or amps, it's light. Varies directly. Okay, we know K is always here. Varies directly as the wattage, which is represented with a W, and inversely as the square of the distance. Watch this now. I'm going to remember. I read it carefully, and I know I have to square that D. Now we've got some information so we can figure out what K is. First of all, let me write K the way I know it's going to have to be. We're going to have K is equal to I times the distance squared. I is the light intensity times the distance squared divided by the watts. Okay. The intensity is 10. There it is. And the distance, we're saying 200 feet, and we're going to square that. So that's 10 times, what's 20 squared? Did I say 200 feet? Oh. 20 squared is 400. And the wattage, right up here, 100. So 20 squared, 400, all of this becomes what? We've got 4,000 divided by 100 equals 40. So we have a K of 40. So here's our equation of variation. Light intensity equals 40 times the wattage divided by the distance squared. What is the intensity if a 75 watt bulb, okay, so we've got 40 times 75 is used at 25 feet. Well, what did we say we had to do with distance? We had to square it. I'm going to leave it at that. You could certainly figure this out, but I'm almost at 35 minutes, more than I should be going. So, there it is. quadratic variations, joint variations, all kinds of variations. See you in class.